Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back. We're about to jump into one of the biggest, most frustrating puzzles in astronomy today.
It really is. It's a genuine mystery.
We found, over 5,000 planets outside our solar system? Something like that?
Thousands, yes. Hot Jupiters, super Earths, you name it. We're getting really good at finding planets.
Especially the big ones, the gas giants.
Yeah.
And if you look at our own solar system, Jupiter, Saturn, they're just swarming with moons.
Absolutely. They're like miniature solar systems in their own right.
So the big question, the one that vexes everyone is, where are all the exomoons?
Exactly. Statistically, they should be everywhere. Billions of them. Yet, as of today, we have 0 confirmed exomoons. Not a single one.
An absence of evidence, as
Yeah.
they say. But that's not evidence of absence. It just means we might be looking for them in the wrong way.
And that's precisely what a new paper we've been digging into suggests. It's by Thomas Winterhalter and his colleagues.
Right. It's on the ArcSIF preprint server, so you can go check it out.
And it lays out this really clear verdict. It basically says, look, the moons are there. The problem isn't the universe. The problem is us. Our technology is, for this specific task, crippled.
So that's our mission today. We're going to unpack why our current methods are failing us, what some are calling the transit trap.
And then we'll get into the exciting part, the proposed solution.
A completely new technological path forward. The paper details how we could build something capable of finding Earth-sized moons up to, 200 parsecs away?
200 parsecs, that's about 650 light years. So we're not just talking about our immediate stellar neighborhood.
We're talking about a serious, wide-scale survey of our corner of the galaxy. So, okay, let's start at the beginning. The transit trap. Why are our best planet-hunting tools failing so badly at finding moons?
It all comes down to the workhorse of exoplanet detection, the transit method. It's given us thousands of planets.
And it's an elegantly simple idea, right? You stare at a star.
You stare at a star and you wait for it to blink.
Exactly. You watch for a tiny, tiny dip in its brightness. And if that dip happens regularly, like clockwork,
Then you can be pretty sure something, a planet, is passing in front of it from our point of view. It's blocking a little bit of the starlight.
it's been incredibly successful. Missions like Kepler, TESS, they've used this to build our entire catalog of worlds.
But when you try to apply that same logic to finding a moon orbiting that planet, the whole thing just falls apart.
Why? A moon would block light too, wouldn't it?
It would, but the problem is alignment. For a planet, you need 3 things lined up: the star, the planet, and us here on Earth.
Okay, that's already a pretty rare alignment.
It is. Now, for a moon, you need 4 things to line up: the star, the planet, the moon, and us. And not just lined up, but at the exact moment the moon is also transiting the star.
So the moon has to be in the right place in its own little orbit around the planet at the exact same time the planet is in the right place in its giant orbit around the star.
Precisely. And the signal you get is incredibly complex. It might be a tiny dip before or after the main planet's transit. It might even just subtly change the shape of the planet's dip.
And you're trying to pick that out from hundreds of light years away.
You're trying to distinguish that from all the other noise. The star itself flickers, you have instrument noise. It's a statistical nightmare. The odds of that perfect celestial choreography happening are just astronomically low.
But that's not even the real killer, is it? There's a much deeper, more fundamental problem with using transits.
That's right. And this is the core of the issue. It's a physics constraint. We need to talk about something called the Hill sphere.
The Hill sphere. Okay, break that down for us.
The Hill sphere is, the best way to think of it is as a planet's gravitational zone of influence. It's a bubble of space around the planet where its own gravity is the boss.
So inside that bubble, the planet's gravity is stronger than the star's gravity.
Strong enough to hold on to something, yes. If an object, like a moon, is inside the Hill sphere, the planet can keep it in a stable, long-term orbit.
And if it's outside?
The star's gravity wins. It'll either rip the moon away or destabilize its orbit until it's ejected from the system. So the size of that Hill sphere is absolutely critical. It dictates how much room a planet has to keep its moons.
Okay, so a bigger Hill sphere means more stable moons, or at least the potential for them.
Exactly. And here is the paradox. The transit method, the one we've been using, works best for planets that are very close to their star.
Right, because they orbit quickly, they transit all the time, so we get lots of data points and can confirm them easily. The hot Jupiters.
Precisely.
Yeah.
But what happens when a planet is very close to its star?
The star's gravity is much, much stronger there.
Overwhelmingly strong. And that immense gravitational pull from the star shrinks the planet's Hill sphere down to almost nothing.
So let me get this straight. The planets that are easiest for us to find with our best method
Are in the very region where it's gravitationally hardest for them to hold onto moons in the first place.
We've been looking in the absolute worst place.
We've perfected a tool that is biased towards finding planets in environments that are actively hostile to the very things we're looking for. It's a fundamental mismatch.
It makes you wonder, was this a huge oversight? Why did we spend decades on a method that was doomed to fail for moon hunting?
It wasn't really an oversight so much as a necessary first step. We had to prove exoplanets were common first. The transit method was the fastest, cheapest way to do that. It gave us the numbers, the low-hanging fruit.
But that fruit was growing in a very barren orchard, so to speak.
A barren orchard for moons, yes. We had to build the catalog of planets first. But now that we know they're everywhere, we need a new tool. We need to shift our focus to planets much, much farther away from their stars.
And there's a really famous example that just drives this point home, right? The whole story with Kepler 1625b.
Oh, yes. The great exomoon candidate that wasn't. For a moment, we thought we had one.
The whole community was buzzing. The initial data from Kepler showed this gas giant, and there was this weird extra little dip in the light after the main transit.
And the main transit seemed to start a bit early, which hinted that the planet was being tugged on by something. A wobble. The signs pointed to a big moon, maybe the size of Neptune.
It felt like we were right on the edge of a historic discovery.
We were. So they pointed the Hubble Space Telescope at it to get a better look, to confirm it.
Yeah.
And the data was messy, it was ambiguous. Some analyses still saw the moon's signal, others said it was gone. It just sort of dissolved under closer scrutiny.
So it was likely just instrument noise or some weird stellar activity that mimicked the moon.
That's the consensus now, yes.
Yeah.
The discovery was essentially debunked. And the whole saga is the perfect illustration of the problem. Even in a best-case scenario, the transit signal is so faint, so close to the noise, that it's almost impossible to be sure.
So if the transit method is a bust, we need a whole new approach. And this is where the new paper gets really interesting.
This is where we stop looking for a shadow and we start looking for gravity itself.
The technique is called astrometry.
Astrometry. It's one of the oldest branches of astronomy, but we're now applying it with a level of precision that is just mind-boggling.
So astrometry is basically just measuring the precise position of things in the sky.
And their movement, yes. When we use it to find a planet, we're not looking at the planet at all. We're looking at its star.
And we're watching the star wobble.
Exactly. A planet's gravity pulls on its star just as the star pulls on the planet. They both orbit a shared center of mass, so the star isn't stationary. It makes these tiny little circles in the sky. If we can measure that wobble, we know a planet is there.
Okay, so that's for planets. How do we apply that to moons?
We just shift our focus. Instead of watching the star wobble, we watch the planet wobble.
Because the moon is pulling on the planet.
Right. The planet and its moon are also orbiting their own little center of mass, their barycenter. So as the planet moves through its huge orbit around the star, it's not tracing a smooth, clean arc.
It's doing a little corkscrew pattern, tiny wobble on top of its main orbit.
A tiny, subtle dance. And if we can measure that dance, we've found the moon that's leading it.
Now this feels like a much better approach. And it directly solves the Hill sphere problem, doesn't it?
It completely flips the script. The beautiful thing about astrometry is that it works best for planets that are far away from their star.
Why is that?
Well, a more distant orbit is a longer orbit, which gives you more time to measure the wobble and separate it from other signals. But more importantly, planets far from their star are free from the star's intense gravitational meddling, which means they have huge, stable Hill spheres. They have all the room in the world to capture and hold on to large families of moons for billions of years.
So astrometry naturally points us to the most promising systems. It's biased towards the gravitationally friendly neighborhoods.
Exactly. It resolves the paradox that crippled the transit method. It lets us finally look in the right place.
Which brings up the obvious question. If astrometry is so much better, why haven't we been doing this all along?
Because of what the paper calls the technological deficit. The principle is sound, but the reality of the measurement is the problem.
The wobble is just too small to see with what we have now.
It's almost infinitesimally small when you're looking at a planet hundreds of light years away. The precision required is just staggering.
Let's talk scale. What can our best telescopes do right now?
Our current champion is the Very Large Telescope Interferometer, the VLTI, down in Chile. It's an incredible machine.
And that's not one telescope, right? It combines the light from multiple ones.
Correct. It links its 4 main telescopes together to act as one giant virtual telescope. And with that, it can resolve an angular wobble of about 50 microarc seconds, 50 yens.
Okay, you have to put that number in perspective for us. What is a microarc second?
Okay, so imagine a single degree in the sky. Divide that by 3,600, that's an arc second.
Already tiny.
Now divide that arc second by another million. That's a microarc second, 1 years.
So 50 microarc seconds is already measuring a movement that is just an absurdly small fraction of a degree.
It is. The common analogy is that it's like being able to spot a single human hair from 2 miles away. That's what 50A's resolution gets you. It's a breathtaking achievement of engineering.
But it's not good enough.
It's not even close. The wobble induced by an Earth-sized moon orbiting a gas giant 200 parsecs away is far, far smaller than that 50A's limit.
And the VLTI gets that resolution by having its telescopes spread out over a distance, a baseline, of about 200 meters.
Right, about the length of 2 football fields. But to find these moons, we need to bridge a monumental gap. We're not talking about a small improvement.
We're talking about a leap. And the paper by Winterholder is very specific about how big that leap needs to be.
It is. It calculates that to find what they call a reasonable number of Earth-sized exomoons out to that 200 parsec distance, you need a resolution of around 1 microarc second.
1/8. So from 50 down to 1. That's a 50-fold increase in precision.
A 50-fold jump. That's not an incremental upgrade. That requires a fundamental rethinking of how we build an observatory.
So if 50 oins is seeing a hair from 2 miles away, what's the analogy for 1 accuracious?
One I've heard is it's the equivalent of measuring the width of a small coin, say a nickel, if that coin were sitting on the surface of the moon.
You're trying to measure the width of a nickel on the moon from Earth.
That's the angular scale we're aiming for. It's measuring a tiny movement of an object that is itself more than 1,000,000 times farther away than the moon. It's an immense challenge.
So how do you do it? How do you get a 50-fold increase in resolution?
You have to go back to the basic physics of interferometry. There's a simple equation. Your resolution is equal to the wavelength of the light you're observing divided by your baseline.
Okay, so resolution equals wavelength over baseline.
Right. We can't really change the wavelength. That's just the starlight we're looking at. So if you want to increase your resolution by a factor of 50...
You have to increase your baseline by a factor of 50.
Exactly. If the VLTI's 200-meter baseline gets you 50 oins, then to get to 1 oins, you need a baseline that's 50 times longer.
200 meters times 50 is 10,000 meters, 10 kilometers.
Several kilometers, yes. This is the heart of the proposal. We have to stop thinking in terms of hundreds of meters and start thinking in terms of kilometers. This is why they call it a kilometric baseline interferometer.
So you're not building one giant telescope. You're building an array of smaller telescopes spread out over an entire valley, maybe.
That's the concept. A whole network of light-collecting stations spread out over kilometers, all linked together optically with a precision that is almost hard to comprehend. They have to act as a single, coherent instrument.
How is that even possible? Keeping the light from mirrors kilometers apart, perfectly in sync.
That's the insane engineering challenge. It involves this thing called optical delay lines, basically long vacuum tunnels with mirrors that can move to precisely adjust the path length of the light from each station.
So the light from a faraway mirror has to travel further, and these tunnels compensate for that, so all the light waves arrive at the central hub at the exact same instant to be combined.
To within a fraction of a wavelength of light, yes. You have to compensate for everything. Thermal expansion, seismic vibrations, atmospheric turbulence. It pushes engineering to its absolute limit.
You mentioned LIGO before, the gravitational wave detector. That's also on a kilometer scale. How is this different?
It's a great comparison for the scale, but the function is totally different. LIGO isn't a telescope. It uses lasers inside its tunnels to measure the stretching of space-time itself.
It's detecting ripples in the fabric of the universe.
Right. This proposed interferometer would be a true telescope. It would be collecting faint starlight from distant objects using these separated mirrors. Its goal is to measure the position and movement of a physical object, not a distortion in space-time.
And an instrument this precise can't just scan the sky randomly. It would be incredibly inefficient. It needs a target list.
Yes, and this is where the synergy with other projects becomes so important. This interferometer isn't a discovery tool, it's a measurement tool. It needs a partner.
And that partner is the Extremely Large Telescope, the ELT.
The ELT, it's under construction right now in Chile, set for completion around 2028. It's going to have a 39-meter primary mirror, the biggest eye on the sky we've ever built.
And its job is different. Its job is just to collect as much light as possible.
Its job is to take the first direct pictures of these very faint, very distant gas giants. The ones orbiting far from their stars, the ones with the big hill spheres that we think are the best candidates for hosting moons.
So the ELT finds the planets. It does the heavy lifting of identifying the targets. It says, okay, look over there. There's a promising gas giant.
Precisely. And once the ELT gives us a target, this kilometer-scale interferometer can then stare at that one planet. It doesn't waste time searching. It just locks on and monitors its position over months and years.
Watching for that tiny 1 microarc second wobble.
That's the tag team. The ELT is the spotter, the interferometer is the sniper. It's an incredibly efficient way to tackle the problem.
So what does this all mean? We're talking about a multi-billion-dollar project, a decade of engineering to build this planetary wobble detector. Why?
Yeah.
Why chase moons so hard when we have thousands of planets?
Because exomoons might fundamentally change our search for life in the universe.
It's about habitability.
It's about redefining what habitable even means. It gives us a pathway to life that has almost nothing to do with the traditional Goldilocks zone.
Okay, the Goldilocks zone being that narrow band around a star where it's not too hot, not too cold, for liquid water to exist on a planet's surface.
Right. It's all based on energy from the star. But for moons orbiting a gas giant, the star is almost irrelevant. They can be far outside the Goldilocks zone in the frozen depths of their solar system and still be habitable.
And this is because of tidal heating.
Tidal heating, it's the real game changer, and we see it right here in our own backyard.
Europa and Enceladus.
Our two most promising candidates for life beyond Earth, Europa at Jupiter and Enceladus at Saturn. They are both ice worlds, far from the sun's warmth. They should be frozen solid.
But they're not. We're pretty sure they both have huge liquid water oceans beneath their ice shells.
And that liquid water is kept warm not by the sun, but by the immense gravity of the planets they orbit.
It's just gravity doing the heating.
Think about the sheer mass of Jupiter. As Europa orbits it, Jupiter's gravity is constantly pulling and stretching the little moon. The side of Europa closest to Jupiter is pulled much harder than the far side.
So the moon is being flexed, like squeezing a stress ball over and over.
Exactly. And that constant flexing and friction in its rocky core generates a tremendous amount of heat. It's like a planetary scale engine churning away in the moon's interior.
And that heat is what keeps those subsurface oceans liquid.
For billions of years, it's a much more stable and long-lasting energy source than the light from a distant star. It creates this tiny local habitable zone right around the gas giant itself.
So if we find a big moon around a big exoplanet, it could have liquid water, even if the whole system is in a deep freeze.
It dramatically expands the amount of real estate in the galaxy where life could get a foothold. It tells us we should maybe stop looking for warm stars and start looking for massive, gravitationally active planets.
Now, the paper is careful to include a reality check here. We all dream of finding another Europa, but that's not what this new telescope would be looking for, is it?
That's a very important caveat, yes. Finding a true analog to Europa or Enceladus is still far beyond our reach. They're just too small.
Europa is only about a quarter the size of Earth.
Right. The gravitational wobble they would induce on Jupiter or Saturn is far, far smaller than the one we're aiming for. We wouldn't be able to see them.
So what is the realistic goal? What are we actually hoping to find?
We're hoping to find the giant versions of these worlds. The paper's target is Earth-sized moons or even larger orbiting gas giants.
A super Europa.
A super Europa. A world with the mass of Earth or Mars would be heavy enough to produce that detectable 1 microarcsecond signal in its parent planet.
And an Earth-sized moon would have some major advantages for habitability, right?
Huge advantages. It would have enough gravity to hold on to a thick atmosphere. If it's in the right place to experience strong tidal heating, it could have vast liquid oceans, maybe even on its surface.
A world like that. It would immediately become the #1 candidate for the first confirmed habitable exoworld.
It would be the holy grail, the ultimate prize. It's a huge technical leap, but the potential reward completely changes our place in the universe.
So let's just wrap up the grand plan here. We have a cosmic mystery. No confirmed moons.
We have a flawed method, transit, that looks in the wrong place, in gravitationally hostile environments.
The proposed solution is a pivot to astrometry. But to make it work, we need a 50-fold jump in precision, down to 1 microarcsecond.
Which is physically impossible without a 50-fold increase in our telescope's baseline.
So we have to build a kilometric baseline interferometer, spread telescopes out over several kilometers to create a single, hyper-precise instrument.
And of course, a project of that scale comes with a price tag to match.
A few $1 billion.
Yeah.
In the same ballpark as the ELT itself.
At least. This is big science. It requires international cooperation, decades of planning.
And a huge battle for funding. What are the real-world chances of something like this getting built?
The biggest hurdle is convincing the world's funding agencies that this is the most important next step. But its greatest advantage is its timing. The ELT comes online around 2028.
And it's going to start finding these perfect target planets.
Exactly. The ELT is going to deliver a catalog of distant gas giants, and the scientific community is going to be clamoring for a way to study them in more detail. The need for this precision follow-up tool will become undeniable.
So the argument will be that the ELT is only half the solution. You need the interferometer to unlock its full potential.
That's the case they'll have to make. It's the logical next step. First, you build the world's biggest camera to find the objects. Then you build the world's biggest ruler to measure them.
A ruler designed to look in the one place we've never been able to look before.
Yeah.
The stable, tidally heated zones far from any star.
It will finally pull the search for exomoons out of the realm of speculation and put it firmly into the realm of observational confirmed science.
Okay, we have covered a lot of ground here, from gravitational bubbles to kilometer-long telescopes. But we want to leave you with one final thought, something to really chew on.
We're talking about building technology on the scale of a small city to measure a gravitational nudge from an object hundreds of light years away. It's an incredible endeavor.
But think about the implication. If it turns out that the most common place for life in the galaxy isn't on a pleasant, Earth-like planet soaking up gentle sunlight.
What if it's on a moon being constantly crushed and stretched and heated from within by the raw mechanical power of its parent planet's gravity?
What does that do to our whole concept of a habitable zone?
Does the real search for life in the universe begin only when we stop looking for the gentle energy of light and start looking for the violent yet life-sustaining power of gravity itself?